Hi, and welcome to this video on forces in braking. These are the key terms for this topic, so make sure you know what each of them means by the time you're done with this video. Picture yourself in 1 or 2 or maybe 20 years time, the proud owner of your very own automobile. As you merrily drive along the road, you notice an obstacle up ahead and decide that it might be a good idea to slam on the brakes. We can split the total distance over which the car comes to rest, its stopping distance, into two sections. The thinking distance is the distance travelled by the car while you react and get ready to press the brake pedal with your foot, and the braking distance is how far you travel once the brakes have been applied. As you might have guessed, the very simple equation which links these three distances is stopping distance equals thinking distance plus braking distance. Before we look at these distances in more detail and how they're affected by speed, let's have a quick chat about reaction times. The average person has a reaction time of about 0.7 seconds. Obviously, when driving, the more quickly we react to events on the road, the better. Our reaction time can increase if we're feeling tired, if we're distracted by, say, a phone conversation, if we've consumed alcohol, or if we've taken drugs. On this last point, remember that even some prescription and off-the-shelf medicines can make us feel drowsy. There's a really easy way for you to test how fast your reactions are in the lab or at home. Ask a friend to hold a ruler vertically in front of you with the 0 centimeter mark resting inside your open hand. Your friend should let go of the ruler at random, and then you should close your hand on it as quickly as you can. The slower your reactions, the further the ruler will have travelled before coming to rest. You could extend this experiment by investigating the effect that listening to music and other distractions have on your reaction time. Have a look now at example 1. We'll start by highlighting the key information in the question. In part A, because the speed is constant, the equation to use is distance equals speed times time. When the reaction time is 0.8 seconds, the thinking distance is just 20 times 0.8, which gives 16 meters. When the reaction time goes up to 1 second, the thinking distance increases to 20 times 1, which is 20 meters. So that means that the increase in thinking distance is just 4 meters, which is about 1 car length. Have a look at part B now, and as you can see, the statement is that talking on the phone will increase your braking distance. Hopefully you'll realise that the correct answer is no here, because the car only begins to decelerate once Mr. Driver has pressed the brake pedal. The braking distance is measured from that point to the point at which the car comes to rest. Here, we can see how the stopping distance of a typical vehicle changes with speed. This diagram, or a version of it, is quite likely to come up in your exam, so it would be well worth pausing the video now just to make sure you're completely happy with how it works. Let's have a look at thinking distance first. When the speed doubles from 20 to 40 miles per hour, for example, the thinking distance goes from 6 to 12 meters. In other words, it doubles too. The same pattern can be seen when the speed increases from 30 to 60 miles per hour. For this reason, we can say that the thinking distance is proportional to the speed of the car. As for braking distance, we can see that it increases much more quickly than the thinking distance when the speed of the car increases. When the speed goes from 20 to 40 miles per hour, for example, the braking distance goes from 6 up to 24 meters, which is an increase by a factor of 4. Likewise, when the speed goes from 30 up to 60 miles per hour, the braking distance goes from 14 to 56 meters, which is again a factor of 4 increase. Because increasing the speed by a factor of 2 causes the braking distance to increase by a factor of 2 squared, or 4, we can say that the braking distance is proportional to v squared. Have a look at example 2 now, which is based on part of this diagram. For part A, we can see that 30 miles per hour is equal to 48 kilometers per hour. To convert that into meters per second, we just multiply 48 by 1000 because there are that number of meters in 1 kilometer, and then divide by 3600 because that's the number of seconds in 1 hour. So that just gives a final answer of 13.3 meters per second. For part B, we know that the thinking distance at 30 miles per hour is 9 meters, and that speed in meters per second is 13.3. Because the driver is travelling at constant speed during the reaction time, the correct equation to use is just distance equals speed times time, which we rearrange to give time equals distance divided by speed, which gives 9 divided by 13.3, which gives 0.7 seconds. For part C, we're just looking at the effect on stopping distance of decreasing the speed from 30 down to 20 miles per hour, which brings us to this nice straightforward answer. Before the last example, we saw that the braking distance of a vehicle is proportional to v squared. Driving faster massively increases your braking distance. Of course, there are some other things that can affect the braking distance of a car as well. Remember that when we brake, we're making use of the force of friction between the car and the road, so anything that affects the size of this force affects the braking distance. That could be the condition of the vehicle, so are the brakes and tyres and so on well maintained, the type of road surface, so is it rough or smooth or loose, the weather conditions, is it dry, windy, rainy, icy, or the size of the braking force. About the last of these points, it makes sense that pressing down harder on the brake pedal will increase the resistive force applied to the wheels by the brake pads, which should in turn increase the friction between the tyres and the road and bring the car to rest in a shorter distance. Sometimes though, if the force applied is too large or if it's applied too suddenly, the car can skid and you can lose control. This is why keeping your speed down is a good idea, because it reduces the braking force you need to apply to be able to stop in a given distance. A moving car has kinetic energy. When the brakes are applied, work is done by the frictional force acting between the brake pads and the wheels. This causes some of the kinetic energy of the car to be converted into heat energy in the brakes. The car slows down and the temperature of the brakes increases, for a time at least. If the brakes get too hot, their effectiveness could decrease or they could stop working completely. Have a read through example 3 now. For part A, we know that the car is decelerating from 30 down to 0 meters per second, so we're going to use the equation here for the acceleration, which is final minus initial velocity divided by time, which becomes 0 minus 30 divided by 10, which gives minus 3 meters per second squared. Because we've been asked for the deceleration here, we should really drop this negative sign, but you wouldn't lose any marks in this point in your exam. For part B, we know the mass and the negative acceleration of the car, so the correct equation to use is Newton's second law, F equals ma, which becomes 1500 times minus 3, which gives minus 4500 newtons, or minus 4.5 kilonewtons. Notice here that we're assuming that the friction between the tyres and the road is the only force that decelerates the car, but in reality, air resistance will do some of the work as well. We're going to finish this video off with two slightly trickier examples. Have a look at number 4. As you can see, Mary writes down that the thinking distance is proportional to v and that the braking distance is proportional to v squared. Let's have a look at the table to work out whether she's right or wrong. When the speed doubles here, we can see that the thinking distance doubles also, but the braking distance increases by a factor of 2 squared or 4. So that means, of course, that Mary is right. One last example now for this video, so just take a few moments to work out what the graph is telling us. For part A, all we need to do is to go to a value of 19 meters per second on the x-axis, draw a vertical line up till we hit the blue line, and then go left to read off a stopping distance of 40 meters. For part B, we can see that the stopping distance of the car at a given speed was longer on Tuesday than on Monday. This could have been caused by anything that affected the friction between the tyres and the road, such as the road surface, the weather conditions, the braking force used, or the condition of the brakes or tyres themselves. That brings us to the end of this video on forces in braking. Drive with care, study with flair, and everything's going to work out just fine.